Hello. We started this topic of renewal processes, and renewal process is an arrival or counting process, and N of T is basically a non-negative integer, and it tells you the number of arrivals or events or renewals or points on the interval from 0 to t with t included. And we take n of 0 to be equal to 0. Now, a renewal process is characterized by IID inter-arrival times. So basically, the sequence of inter-arrivals is an IID sequence. And here we will assume that the probability that u is greater than 0, that this probability is equal to 1. The occurrence times basically are the sums of the inter-arrival times. So T1 is U1, T2 is U1 plus U2, T3 is U1 plus U2, U3, and so on. In the previous lecture, we said basically that we have two events that are equivalent, n of t greater than or equal to small n, if and only if the time of the nth arrival is less than or equal to t. And we use this fact to obtain the PMF of n of t. And here f sub n of t is the CDF of the of Tn. Again, Tn is the sum of n inter-arrival times, and those by definition for a renewal process are IID. All the moments, given basically this assumption, all the moments of n of t are finite, and we are interested in the first moment, denoted small m of t, and is called the renewal function. And the renewal function, also n of 0 is 0, and it is given by this sum here. It's sum for n from 1 to infinity, fn of t. And we will basically continue the topic of renewal processes by investigating basically small m of t. We can write it in a number of ways. Some of them will be very useful in particular contexts or problems. So m of t is the expectation of big N of t. So what we can do, and this is a common trick when it comes to renewal processes, is that we condition on the first arrival. So what we do is that rather than talking about this expectation of big N of t, we say that we will condition on the first arrival occurring at alpha. So remember that U1 is equal to T1 is equal to alpha. And so we will deal with this conditional expectation. And of course, this is our main concern, and so we need to take the conditional expectation, multiply it by the PDF of the inter-arrival time, and then integrate from 0 to infinity. Then we can split the integral into two parts, from 0 to t and from t to infinity. What is the meaning of this second integral? Now alpha, which is the time of the first event, is greater than t. The time of the first event, alpha, is greater than t here. So this means that what is n of t? So n of t is the number of arrivals up to time t. But the first arrival occurred at alpha, which is greater than t in this interval from t to infinity. So this means that n of t is equal to 0. And so basically the integrand here is 0, and this term is equal to 0. So the survivor will be the integral from 0 to t. Okay. Now we have expectation n of t given that u1 is equal to alpha, and now alpha is less than t. So basically we are studying at the instant t, and the first arrival has occurred at time instant alpha. Okay, the first event. Okay, so here is a claim. The claim is that basically n of t, okay, n of t is equal to 1 plus n of t minus alpha. So what is going on here? Basically, alpha tells us the time of the first arrival. So at all time instants before alpha, we don't have any arrival by definition because alpha is the time of the first arrival. At the time instant alpha, we have our first arrival. So if we start counting from that, okay, so now here is the thing, that in the definition of a renewal process, the next arrival, so that, which is characterized, so now we have an arrival at time instant alpha. The next arrival will happen after a time that is given by the PDF of the inter-arrival time big U. And the inter-arrival times are IID, which means that once you have an arrival, you can think that your process has started in U. It's as if, you are basically restarting the process from the beginning. So if your first arrival occurs at instant alpha, and then you study what is the number of arrivals at time t, what you can say is that basically there are no arrivals here. There is one arrival at alpha, and then, you can, as if you shift the time origin, and you say, now I will ask myself what is the number of arrivals on the time interval t minus alpha. Note that because the inter-arrival times are independent of one another, then basically immediately after an arrival, whatever happens in the future of the random process is independent of the past. You just need to keep this one into account because you already have one arrival here at time alpha. So that's basically the trick here. The trick that conditioning, if you condition on the first event occurring at time instant alpha, then basically the expectation of n of t given that u1 is equal to alpha is 1. So this 1 is basically the first event that has occurred at time instant alpha. And then after that, things become independent, as if the process starts in U. And that's the reason it's called a renewal process. Okay, so immediately after the event, it's as if, things are starting again. The only thing now that the boundary condition, rather than being n of 0 equals 0, the boundary condition will be whatever number of arrivals that you already have in the system. Okay, so this is the idea, and hence this expectation here can be written as 1 plus the expectation of n t minus alpha, and that's small m of t minus alpha. You can split this integral into two parts. So the integration 1 times the PDF, that's the CDF, and then this integration of m of t minus alpha, the PDF of alpha, that's the convolution between the renewal function and basically the inter-arrival PDF. So now we have a very important integral equation for the renewal function. So we have that m of t, which is the expectation of big N of t, is equal to the CDF of the inter-arrival time plus basically the convolution between the PDF of the inter-arrival time and m of t itself. Okay, so that's an integral equation that basically m of t satisfies. Okay, and now another thing that you can do is basically to try to solve this integral equation using the Laplace transform. The Laplace transform of m of t is big M of s, and here, like, basically I am saying that we will assume here that m of t is differentiable, and it has a Laplace transform big M of s, and the Laplace transform of its first derivative is S big M of S. Now, if you take the Laplace transform of this equation, M of t becomes M of S. The Laplace transform of the CDF is the Laplace transform of the BDF divided by S. And the Laplace transform, like the Fourier transform, it converts convolution into a product. And so the convolution between the BDF and M of t, it will give you basically the product of the Laplace transform of the interarrival time, PDF. So that's big phi of S, and then M of S again. And what, one thing that you can do here is basically to multiply and divide by S. And if you do this, basically this becomes the Laplace transform of the CDF of the interarrival time. And M of S will be the Laplace transform of the first derivative of the renewal function. So in addition to our original equation, so like if you do the inverse Laplace transform, you can write down M of t also as the CDF plus a convolution. So you can write down the convolution as the convolution between the PDF and the renewal function, or by doing this trick of multiplying and dividing by S, we can write down this term here as the convolution between the CDF and the first derivative of the renewal function. Again, sometimes this is useful, sometimes that is useful. But if we go back to the Laplace transform, we can actually put big M of S on one side and put a big phi U of S on the other side. So basically, from here, I can move this to the other side. And so we have 1 minus big phi of S M of S is equal to 1 of S phi of S. And so basically, you can, remember that if the real part of S is strictly greater than 0, then the Laplace transform, which is the expectation of e to the minus su, will be strictly less than 1. Okay, and so this thing here is strictly less than 1 in magnitude. And okay, so the magnitude will be strictly less than 1. And basically, this thing is never 0. You can divide by 1 minus phi of S. And because the magnitude is less than 1, actually you can do a series expansion and write 1 over 1 minus big phi as 1 plus phi squared plus phi cubed, and so on and so forth. Okay, and so you get basically another expression for big M of S, which is given by this infinite series here. Okay, and again, like if you just use S with a real part that is greater than 0, then you are sure about convergence. We will assume that we have the formula for the renewal function, which is this one here. We will assume that if you take the Laplace transform of this formula, then you can basically interchange the Laplace transform and the infinite sum, which means that the Laplace transform of the sum is the sum of the Laplace transforms. And so we can basically write down something like that. And also for differentiation. So you can assume here that we can interchange Laplace transform and infinite summation, and you can interchange the derivative operator and basically infinite summation. Okay, so we will take these for granted and we'll use them later. Okay, so we have like lots of results here. So let's summarize them. We have M of t is equal to this summation. Okay, so this is from the previous lecture, and this summation converges for every finite t. You can take the derivative. Or the differential of both sides, and for the differential of the summation, yeah, we will take it for granted that we can interchange the order of infinite summation and differentiation. Okay, M of t satisfies an integral equation. It is equal to the CDF plus the PDF convolved with M of t itself, or it is the CDF plus the CDF convolved with the first derivative of M of t. Okay, so we can basically write down things like this, and by taking the Laplace transform of this, we have M of S is equal to summation n from 1 to infinity. the Laplace transform of the CDF of T of n. That's as we did in the previous lecture. This is phi u of s to the power n, and since this is a CDF, then we divide by s. Okay, and basically, you have here s. You can move s to the other side. Sm of s is equal to this thing again. It converges if you choose the real part of s to be strictly positive, and it will give you phi u of s over 1 minus phi u of s like this. Okay, which you can rewrite it again depending on the situation. You can write it as 1 over s phi u of s over 1 minus phi u of s. Okay, so we will take basically those relations. We do not like sort of there are many things to be justified here in terms of the ordering of the operations. But as I said last time, that basically especially when it comes to the Laplace transform, we rather than being basically drowned by these details, we need to focus on the topic of renewal processes, which is a challenging in and of itself. Okay, and so we can consider those guys to be your starting points, and again we will assume that m of t is differentiable and that it has a Laplace transform, that its first derivative has a Laplace transform, and now let's basically make use of these. Any questions? So our first very important topic is basically the topic of residual time. Okay, and the idea here is the following. So this is the time axis, okay, and you investigate the time axis at time instant t. Okay, and then you ask yourself, what is the difference between t and the time of the next arrival? Okay, so there is before t there is some arrival, right? Before the time instant t, there is some arrival. Okay, so this is arrival, and you ask yourself about the time, so r of t, which is the time to the next arrival. Okay, so this is called the residual lifetime. So we have two arrivals, and again, like you inspect the system in between the two arrivals, and you ask yourself, what is the remaining life? What is the time to the next arrival? What is the residual time? Some people call this the forward recurrence time or the forward excess. It's like going to the bus stop. Okay, so you can imagine that the buses arrive at a bus stop as a renewal process, and you arrive at the bus stop and you ask yourself, what is the remaining time till the next arrival of a bus? Okay, so it is a fundamental problem in renewal processes, and like for those of you taking wireless communications, like we will use this idea of a residual time or remaining time in investigating admission into a cellular system. So it is a very practical problem, and it arises in many fields. Okay, so here you need to understand everything, and in the coming homework I will ask you about the age process, or the age. So the age of the process, which is W of t, it's if you inspect the process at time t, you ask yourself, what is the time difference between now and the previous arrival? Okay, so I will leave this as an exercise. It's not an exercise, actually. It is part of the homework, and to be able to solve it, you will need to understand very well the residual time. Okay, so this is worth of basically investigation and spending some time like going into the details and understanding what is going on. Okay, so the residual time, again, it's R of t. You must specify a t. You must give me a t. T can be equal to 10 seconds, 10 years, 10 minutes, any time, any point on the time axis. And we ask ourselves, okay, what is basically t of n of t plus 1. So at time t, there is a number of arrivals in the system. Okay, so this is number of arrivals up to t. Okay, so you ask yourself, what is the difference between t of big N of t plus 1? So if n of t is the number of arrivals at t, we ask about the immediately next arrival, big T of n of t plus 1 minus t. So this will be the residual time. Okay. The residual time is a tricky quantity because, if you look at its definition, it's again big T n of t plus 1 minus t. It depends on n of t. It depends on, so if n of t is 3, we are talking about t4 minus t. If n of t is 7, we are talking about big T of 8 minus small t, and so on and so forth. Remember that n of t itself is a random variable, and in the previous lecture we obtained its PMF. But the point is that it is a random variable. So this quantity is not as straightforward as it may look, again, due to the randomness of n of t. If I tell you, I will inspect the system at time t, n of t is itself a random variable with a certain PMF. Okay, so this is very important. And it tells us that, if you want to compute the PDF or CDF of the residual time, perhaps it's a good idea to use the law of total probability and to involve all possible values of n of t. Okay, and this is exactly what we will do. We will investigate the CDF of R of t, and we will apply the law of total probability by basically involving n of t equals to small n, which can be from 0, any non-negative integer from 0 to infinity. Again, because, it is the time to the next arrival. So what is the next arrival? Is it big T of 7? Is it big T of 23? Well, it depends on what at time t, how many arrivals has occurred so far. This is a random, basically, quantity that can take, basically any non-negative integer value. And so again, the trick is law of total probability, and you basically have n of t is equal to n. It will make basically things sort of better conceptually if we fix big N of t equal to n, and of course the price is that we will have to do a summation that involves all possible values of big N of t. Now, what is the residual time? So the residual time is n of t plus 1 minus t, and so this thing is equal to t of n plus 1 minus t if n of t is equal to small n. So once you involve this event, that big N of t is equal to small n, then you can replace big N of t plus 1 by small n plus 1. And so the residual time will be this quantity, which can be written as that the time of arrival n plus 1 is less than or equal to t plus x. And we will basically separate this summation into two parts. One of them is the term small n equals 0, and then the remaining terms will be in the other sum. Okay, so small n equals 0 is like sort of a special case, and it tells you that at time t, basically no arrivals. Okay, so this is the term in which n of t is exactly equal to 0. So now, if n is equal to 0, now this is the term that t1, which is equal to u1, is less than or equal to small t plus x, and n of t is equal to 0. What is this event? So this event is telling you that u of 1 is less than or equal to t plus x, because u of 1 is the same as the time of the first event or first arrival. But actually this event is more, because n of t is equal to 0. It means that we are sure that the first arrival has occurred after t, because if the first arrival has occurred at t or less, then n of t would be higher than 0. So the fact that n of t is 0 means that u1 is greater than t. So basically the event that we have here is that the first arrival is strictly greater than t, but is less than or equal to t plus x. This event means that basically the residual time is less than or equal to x. So the residual time will be the time between t and the time of the first arrival. And because n of t is 0, then it must be the case that big U sub 1 should be strictly greater than t. And so this probability here can be written in terms of the CDF of the inter-arrival time. And specifically, it is big F of t plus x minus big F of t. You know, because we basically compute this probability between these two guys. It can be written as the difference between the CDF evaluated at t plus x and the CDF evaluated at t. Now, the remaining term will involve everything, basically starting from small n from 1 to infinity. And now let's basically do the same. Let's do the same basically trick here. So n of t is equal to n. So at time t, there has been n arrivals so far, and we have basically this is t of n, and the next arrival will be tn plus 1, and this is basically the residual time, and this u of n plus 1 is the time, you know, basically between the nth arrival and arrival n plus 1. Now, we will do the law of total probability again. Okay, so basically here in this summation, okay, so we will use law of total probability again. So we first involved big N of t is equal to n. Now we will involve the time of arrival n. Okay, so we will take probability t of n plus 1 less than or equal to t plus x, n of t is equal to n. What we will do is that we will condition on t of n equals alpha, that the nth arrival basically has occurred at time alpha. We multiply by basically the PDF, and then we integrate from 0 to infinity. Okay, so we will do this again, law of total probability again, a very basic law of probability and very useful. Okay, and now let's think about this integral. So this integral is written here. This integral is written here from 0 to infinity. But if you see my my derivation here, it is from 0 to small t, which means that it's like, you know, again, like if you do things in slow motion, what you will do is that you will say, okay, I will take this integral from 0 to infinity, split it into an integral from 0 to small t and integral from small t to infinity. Now, in the integral from small t to infinity, this mean, you know, what is the meaning here? So alpha, remember, alpha is basically the time of the nth arrival. and the time of the nth arrival is now greater than the time of the nth arrival greater than t. Now let's see the probability that we have here. The probability is basically the probability that tn plus 1 is less than or equal to t plus x, and then n of t is equal to n, given that tn is equal to alpha. Now think about this. So the event here is that n of t is n. The event here is n of t is n, which big N of t is a small n, which means that at time small t, basically the number of arrivals so far is equal to small n. Now we are conditioning on the time of the nth arrival. If the time of the nth arrival is strictly greater than t, it means that big N of t cannot be equal to small n, because the nth arrival will happen after t. So basically conditioning on tn equals alpha, if alpha is greater than t, then basically this probability is exactly equal to 0. Because the probability is, we are saying that, what is the probability of having this event that n of t is equal to n? And we are conditioning on the nth arrival occurring at a time alpha that is basically greater than t, which means that at time t we don't have the nth arrival. The nth arrival will happen after that, so big N of t cannot be equal to small n. So basically the second integral from t to infinity, this is equal to 0, and basically your integral here is from 0 to small t. Okay, so again, you can do things in slow motion, and again, you basically apply the law of total probability again. Take this probability, make it conditioned on the time of the nth arrival, okay, and then of course multiply by the PDF of the nth arrival time and integrate, and then split the integral into an integral from 0 to small t, from small t to infinity, and then make an argument or convince yourself that the integral from small t to infinity will be 0, and you are left with the integral from 0 to small t. Okay, so this is what we have here. Now, the event, okay, so look here, what is the event? Basically n of t is equal to n, okay, and the time of, so the residual time, basically our original event is that the residual time is less than or equal to x, okay? And so what is the residual time? So the residual time is, so r of t is tn plus 1 minus tn minus 1, tn plus 1 minus small t. So we want this thing to be less than x, so we want basically tn plus 1 to be less than t plus x, okay? And what is tn plus 1? What is this tn plus 1? And tn plus 1 is equal to tn plus un plus 1. And now we are conditioning on the time of the nth arrival. And so this guy is alpha plus un plus 1. Okay, and so this event here is that un plus 1 plus alpha is less than or equal to t plus x, which can be written as un plus 1 less than or equal to t plus x minus alpha. But this is not actually this event here. This event also involves something that is very important, that big N of t is equal to n, which means that at time t we have n arrivals. So arrival n plus 1, event n plus 1 must occur after t. So basically un plus 1 plus alpha, which is tn plus 1, must be greater than t, which means that un plus 1 must be greater than t minus alpha. So again, we have basically a sandwich for un plus 1 must be greater than t minus alpha, must be less than or equal to t plus x minus alpha. And so basically this can be written in terms of the CDF. Note that the fact that we have un plus 1 here is not important, because the inter-arrival times are identically distributed. Okay, so all of them, regardless of small of n, the distribution is the same, and so this probability is just this difference between the CDFs. Okay. But again, we have an infinite sum and we have an integral. and what we will do is basically we will write down the PDF d alpha is basically the differential of the CDF, and then by Tonelli, everything here is, but basically we are dealing with the PDF and the probability. Things here are non-negative, and so basically by Tonelli we can do things in any order of our choice, and we can take this summation with this D of the CDF, and based on the previous slide, this is equal to dm of alpha. Okay, and so we can rewrite basically this second, this integral as an integral in volume. So the summation now will disappear, and rather than having an infinite sum and an integral, we have an integral, and then again the infinite sum applied to the PDF d alpha can be written actually in terms of the first derivative of the renewal function small m of t, which is the expectation of big N of t. Okay. And then what we will do is that we will basically just to do some simplification. I mean, we are sort of done, but I mean, to report the result in a way that typically appears in references, what I will do here is that I will add 1 and subtract 1. I will add 1 and I will add 1 and subtract 1. Okay? Then basically minus 1 and this CDF here. Okay, so here we have minus 1 and the CDF. So here the green guys are this green guy, and then there is an integral from with minus FUT minus alpha. So basically those are the guys with this red thing. So here we have this red arc also here, and then we will have basically 1 multiplied by the integral of the first derivative of the renewal function, which will be so basically this integral is m of alpha, and then you put alpha from 0 to t. So this is m of t minus m of 0, and m of 0 is equal to 0. So this is m of t minus 0, which is m of t. So basically the integral now with this plus 1, the integral will give you an m of t. Okay, and then we can actually combine. So there is basically, when we dealt with the term corresponding to small n equals 0, we got this basically CDF. We can combine it with m of t, making use of the integral equation of the renewal function. So remember that the renewal function m of t is equal to the CDF plus the CDF convolved with the first derivative of the renewal function. So if you look, if you basically have this one here, if you do the integration, you will get m of t, and if you look at these two terms together, you have m of t minus the CDF. It's as if you take this to the other side, and then you have something in the form of the convolution of the CDF and the first derivative of the renewal function. But what is this last term here? This last term is the convolution between the CDF and the first derivative of the renewal function, and it comes with a minus sign. So these two guys cancel out, and we are left with basically this guy here, and this integral will survive. And this is the CDF of the residual time, and as you can see, it depends on t. Generally speaking, it depends on t. So this is a quantity that actually it's parameterized by t, and it depends on t. The distribution depends on the time of inspection. So you enter into the system, you examine the system at time t, and you ask yourself, what is the remaining time to the next arrival? Well, basically things, generally speaking, will depend on t, and the CDF is not a nice quantity at all. The CDF of the residual time is basically the CDF of the inter-arrival time evaluated at t plus x. So here we have r of t less than or equal to x. Here we have f of u t plus x minus, and then we have an integral, and this integral will involve the CDF of the inter-arrival time, and this monster here, basically the first derivative of the renewal function, which is the expectation of n of t. And so this is basically the CDF. You need to basically make this proof write it down yourself, basically doing each step and making sure that you understand what we are doing, basically given the constraints that we have here. Like, so again, like, how can you justify taking the summation, dm of alpha as this one? Yeah, this is something that we take for granted. This is not something that you need to think about. Okay, but the steps that are here, other than this one, are very important to understand, and so that you can solve more general problems. Okay, the complementary CDF is basically 1 minus the CDF, and it will basically be given by this. And what is the PDF? How can we obtain the PDF from the CDF? So basically we differentiate. Okay, so here the PDF from the CDF, we differentiate with respect to x. And so this CDF becomes a PDF. Now let's look at this integral here. What are basically the things here that depend on x? We have something inside the integral. We can assume that the Leibniz differentiation under integral sign is valid, and so basically we can differentiate the integrand, and if you differentiate the integrand, this differential here will give you minus the PDF, and minus with minus gives you plus, and so you get the PDF here multiplied by the first derivative of the renewal function. Okay, so this will be the PDF. Again, that is not something that is like it's not good looking, right? It looks like a complicated quantity, and it is. Now, two things. First is the typical step I talked about in the previous lecture, which is like you do something like this, and then you ask yourself, well, I know very well the results of a Poisson random process, and the Poisson random process is a special case of a renewal process. So for a Poisson random process, basically the residual time is known to be basically to have a PDF that is exactly the exponential distribution of the inter-arrival time. Okay, so so again, perhaps you know this from a previous course, or if you don't, here you are hearing it. That basically for a Poisson process, if basically Poisson lambda, then basically the inter-arrival time u is exponential lambda, and r of t is also exponential lambda independent of t. Okay, so basically somehow, because in the Poisson process we use the exponential, and for absolutely continuous random variables, remember, the exponential distribution is the only one with the memoryless property. Okay, so somehow this memoryless property will basically make R of t have a distribution independent of t. And so, if you study the residual time in a Poisson process, like something like what you do in 241, perhaps you did the proof in a way that is much simpler than what I am doing here, and perhaps you did not use the law of total probability. And the reason, so it does not mean that the proofs are correct and everything. It is just that you are exploiting the memorylessness of the exponential random variable. But for the general case in which the inter-arrival time has a general PDF, then things become complicated, and here you apply the law of total probability once by involving big N of t is equal to small n, and then you do again the law of total probability by conditioning on the time of the nth arrival. Okay, and so things here look complicated again because we don't have the exponential. Of course, the general case, if you use that, for a Poisson process, n of t is equal to lambda t, and expectation of n, small m of t is equal to lambda t. This is the expectation of n of t, and so the first derivative of the renewal process is just a constant, which is lambda, and so if you put lambda here, So again, for a Poisson process, this thing here is not even a function of lambda. It's the constant, is not a function of alpha. It's just the constant lambda. And you put it there, and you find that anything that is related to t will cancel out, and you are left with a PDF, which is exactly the PDF of the inter-arrival time. Okay, which again is so cool. If your process is a Poisson process, the remaining time, the residual time till the next arrival, the PDF of this thing is exactly the PDF of the time between two successive arrivals, which is the exponential lambda, and this is independent of the time of inspection, small t. But for a general renewal process, things will depend on small t. Now, there is something, some people call this a paradox. Okay, it is not really a paradox, but you may feel that the residual time is always smaller than the inter-arrival time. Okay, so you may have the wrong feeling that R of t is less than or equal to the inter-arrival time, right? You can say, oh, inter-arrival is the time between two successive arrivals. R of t is the time between some time instant t and the next arrival. It seems that, that it's like this, and it seems like, the expected value of R of t should be less than expected u. Again, this is wrong. Okay, this is wrong, and it's wrong because the conceptual picture that tells you this involves conditioning on n of t, while the residual time is not computed with n of t being equal to a specific number. What do I mean by this? So let's go back to actually how we started the derivation. Okay, so there is this picture here. Okay, so there is this picture in which there is t, there is big N of t here, okay, and it is equal to n, small n, and before that there is the nth arrival, and after that there is arrival n plus 1. Between the two arrivals there is un plus 1. Between t and the arrival n plus 1 we have r of t. And so you may say, yeah, see, the residual time is less than the inter-arrival time. So something like when I say that in exponential, in the Poisson process, basically that R of t, it has the exact same distribution as u, it looks awkward. Well, it looks awkward again because this picture that you have right here is a picture, in which, like you say, n of t is equal to n, tn is equal to alpha. But basically, R of t is a complicated quantity. It is big T, n of t plus 1, and you should investigate all possibilities for big N of t. You should investigate all the possibilities for big N of t. It's again, like this proof, it's the one I prefer because it explicitly starts by applying the law of total probability and telling you that you need to sweep through all the possibilities for big N of t, because that's the definition of R of t. R of t is not, is not that you fix big N of t at a specific value and then you investigate this figure here, which again is very misleading, and it gives you the impression that definitely, if I arrive at a bus stop, then the time I wait till the next arrival is less than the time between two successive arrivals. Wrong, because we do not define the residual time like this. So the paradox here, again, I think it is this, and some very respectable references deal with it as a paradox, but it is basically, we don't define R of t is defined in this complicated way. So we want it to be a general thing that is not a function of the exact value of n of t. Okay, so that's the idea of defining it like this. Okay, and so it involves this infinite summation, and so in fact, if you compute the expected value of R of t, you can do it in a number of ways. You can use the PDF, or you can use Ward's identity, as I will use later in the lecture. The expected value of R of t may be greater than, may be equal, or may be less than the expected value of u. It may be greater than the expected value of u. So if you don't like the process and you say, it does not make sense that the remaining time is also exponential, the exact same distribution as the inter-arrival time. And so basically, if the inter-arrival time has a mean value of 1 over lambda, then the residual time has a mean value exactly 1 over lambda. Yes. And worse, if this makes you unhappy, then get ready for this. Sometimes actually the expected value of the residual time may be greater than the expected value of u, and sometimes it's less than u. Less than u, it's the case in which your intuition wants you to basically believe in this. Believe that the time between t and the next arrival should, on average, at least be less than the inter-arrival average time. But it's not. It depends on the distribution. It depends on the inter-arrival distribution, and it depends on the fact that the residual time is a monster. Again, it is this thing here. You should show respect to this. Okay, it is not for a particular n of t. Okay, and some people give like other explanations, like that basically whenever you inspect a renewal process, basically if you think of t as a random instant of time, it is more likely to visit the time axis basically on intervals with a larger than average inter-arrival time. Okay, some people make arguments. Again, you can go and check this thing here. Some people call it the bus stop paradox. It has actually several, the inspection paradox. It has several names. You can just Google it, inspection paradox, or bus stop paradox. Or it depends on what reference you are talking about. Okay, but for me here again, R of t is just complicated, and you may think that perhaps it's even ridiculous to define R of t like this. I don't see ridiculous at all. Basically, this is a definition so that you get something that does not make you track the exact value of n of t. So you want to make a statement that is sort of it does not, because if we make R of t dependent of n of t, then there is an answer if n of t is 1, there is an answer if n of t is 2, there is an answer when n of t is 3, and so on. But we sort of average over all possible answers. Okay, it seems to me like a fair thing to do, and it will make R of t something again that is sort of something that is living, that depends only on t. It depends only on small t, okay, and not on t and big N of t. Okay, so this is very important. Spend some time basically to think about this. Okay, any question? Okay, so in applications, like for example, if you are using basically remaining or residual times in analyzing a cellular system or doing something practical. Now it seems that this PDF for R of T is like very complicated, and it depends on T, and we want something simpler. So in applications, typically you will assume that basically T is very large. Okay, so typically, and this is what I have seen in applications like in wireless communication, like basically people, you take the limit as T goes to infinity. You assume that some significant amount of time has elapsed, and sort of you wish that basically after a very long period of time, things will sort of become independent of time. Okay, so again, in practical applications, people will tend to use the steady state distribution, which is sort of the distribution as T goes to infinity. Now, it is like the evil thing is to show that such limit exists. Who says that actually if you take the limit as T goes to infinity, that actually you will find the limit? Okay, so here again, renewal processes are long, life is short, and so what I will do is that I will assume that the limit exists, and I will try just to obtain that limit. But what you find here written on one page maybe actually explained rigorously using several perhaps many pages, again, because if you want to do things rigorously, you need actually to argue that the limit even exists. Okay, I mean, who knows, perhaps if you take the limit of the PDF of R of T as T goes to infinity, perhaps there is no limit even. Okay, but here we will take it for granted, and so I will just like proceed as if this limit exists. So I will operate on the complementary CDF. From the previous page, it looks like this. Now take the limit. The limit of this part is easy. That's a CDF, and we are assuming that our inter-arrival time is a it's an ordinary random variable. It's non-defective, and so as T goes to infinity, the CDF will go to 1, and so 1 minus 1 will be 0, and so this will disappear. And the challenge now becomes the limit of this guy here. So this guy here is the convolution between the first derivative of the renewal function and this other function. Okay? And the way to go here, and again, here we are already assuming that the limit exists, and we can apply something like the final limit, the final value theorem of the Laplace transform. So remember, if G of T has a Laplace transform, which is G of S, then if you are interested in examining the limit as T goes to infinity of G of T, assuming that this limit exists, then actually you can play this game in the S domain by investigating the limit as S goes to 0 of SG of S. And if needed, you can basically investigate the limit as S approaches 0 from the right of SG of S. But again, like, we will not basically pay big attention to this issue here. So rather than having the limit as T goes to infinity, we will say, okay, let me take the Laplace transform of this thing, multiply by S, and take the limit as S goes to 0. And then what is the Laplace transform of a convolution? It is the product of Laplace transform. So we have the Laplace transform of this thing here, and the Laplace transform of the first derivative is S multiplied by the Laplace transform of M of T. And on the previous page, we showed that basically Sm of S is equal to the Laplace transform of the inter-arrival PDF over 1 minus this big phi of S. And now let's basically try to do the limits. So that so the trick here is basically to apply the limit like as if you have a product of three functions. The Laplace transform, the limit as s goes to 0 is 1. Okay, and so it's like also the moment generating function and characteristic function. So the limit is 1. The limit is 1 minus phi u of s over s. This is like from the previous lecture. This is if basically this guy is finite. So we are assuming that this guy is finite. Then the limit as s goes to 0 of this quantity is the expectation of u. And so the limit as s goes to 0, s over 1 minus phi of s is 1 over expected value of u. And so basically we can basically make use of these two results and rewrite basically. So now we have the limit as s goes to 0 of this Laplace transform. What we will do is that we will use the final value theorem again, but in reverse. Okay, so this is the idea that we will. So again, it's like you apply the final value theorem, you get terms in the S domain, you do some of the limits, as S goes to 0, and then you say, okay, so now I am done in the S domain. Let's now go back to the time domain and do things as t goes to infinity, and this is what you will get here. Okay, now the game here again, it like assumes that every limit I talked about actually exists. Okay, and this is what we will do. Now the last thing is that you want to take the limit as t goes to infinity. Before doing that, we can do a change of variables. If you call u plus x equals v, and so if u is 0, then v, so u is 0 means that v is equal to x, and if u is equal to t, then v is equal to x plus t, and the du is equal to dv. So again, it's just a conventional change of variables, and you get this integral here. Now you can apply the limit as t goes to infinity, and it will make this other limit of integration infinity. Now this is the limit of the complementary CDF. This is the limit of the complementary CDF. Okay, so it's an integral. It's an integral from x to infinity of something. Okay. So the complementary, the asymptotic complementary CDF, it's the integral from x to infinity of something. So what is this thing? It's the PDF, right? So if you have a PDF that depends on basically so have the PDF. Now you ask yourself, what is the probability that my random variable is greater than x? Well, it's the integral from x to infinity, the PDF, and then you choose any dummy variable of integration, dv, right? This will give you the complementary CDF. So, so basically, we studied here the asymptotic of the complementary CDF. We ended up with the integral of something from x to infinity. So this thing must be the asymptotic PDF. Okay, so the asymptotic PDF is whatever you find inside this integral, and it is given by this expression. So it's 1 minus the CDF over the expectation of u. And you can check that actually this thing is indeed a valid PDF. There is no t now. Okay, there is no t now. So again, in applications, because the PDF or CDF or complementary CDF of a renewal of the remaining time of a renewal process is like sort of complicated. So what we do is we focus on the limit as t goes to infinity, and there is a challenge of proving that that things actually have a limit, we will basically gloss over this technicality. We will just assume that the limit exists, and we will play the game of the final value theorem to obtain this limit. And this is basically the asymptotic PDF. Okay, and if needed, you can just, of course, use this result. But you know, you can find the problems in which, like, some of the limits used here are useful. As I said, like in a previous lecture, you know, the amount of rigor that is expected of you in the homework is basically determined by the amount of rigor in the lectures. Okay, so if I am rigorous, if I do something rigorously, you need to be rigorous. If I do something like this, then you do it like me. Okay, so there is no worries, you know. So you can basically do these steps as I did them. I cannot demand that you like sort of do things more rigorously than what I am doing here in the lecture. Okay, so any question? Okay, strong law for renewal processes. So, you know, let's now like sort of mix the chapter on convergence of random variables, and now we have renewal processes. And well, there are like sort of initial results, and the proofs of those results are in the notes if you are interested in basically reading them. So these are the statements that Tn converges almost surely to infinity as n goes to infinity, which sort of makes sense, right? So like you have the time, this is the time of the first arrival, time of the second arrival, time of the third arrival, time of the fourth arrival, and so on. So you know, the times are increasing, and so yes, Tn again converges almost surely to infinity, which means that Tn becomes arbitrarily large as n gets larger and larger. Okay, so if you ask about the arrival number million and arrival billion and so on, you expect that you get greater and greater numbers. Also, n of t converges almost surely to infinity as t goes to infinity. So n of t, the number of arrivals in the system basically grow without bound. It is basically an arrival process, and you keep counting those arrivals, and those arrivals will keep coming and coming and coming and coming and coming and coming. Okay, and so you expect basically that n of t will keep growing without bound. Okay, so these two statements, I mean, you can just basically they tell you that the time of the nth arrival grows without bound as small n gets larger and larger, and the number of arrivals in the system will just grow with time. To make the number of arrivals in the system finite, and this is the advantage, if you are not swallowing these things, hopefully the proofs will convince you. So actually one proof of this statement here is to ask this question: when is big N of t finite? What does it mean that the number of arrivals will be some finite number and that's it, even for any arbitrary large time t? It means that there will be an arrival, right? And then the inter-arrival time, the time to the next arrival, is infinity. Okay, so so you start getting arrivals, and then one inter-arrival time is actually infinity, and so there will be sort of the last arrival in the system, because the coming arrival is after infinity. Okay, but we are dealing with so basically n of t. So let me write this here. N of t is finite or n of t can be finite as t goes to infinity if we allow the use of defective random variables for u. Okay, which means that basically in this case, the probability that u basically less than infinity will be strictly less than 1, and there will be a probability that u is equal to plus infinity will be something that is non-zero. So you can use, you can use defective random variables. Basically, we will see this in Markov chains. From the previous lecture, I said that, basically we will assume that our inter-arrival times are basically ordinary random variables. Okay, so ordinary random variables, they do not take the value plus infinity because plus infinity is not a real number. Okay, so but there are situations in probability. We are not undergraduates here. There are actually very useful contexts in which you need a defective random variable, which basically which can take values like plus infinity with a strictly positive probability. Okay, so you can do this, and again, just wait for Markov chains. But here, so those statements, are guaranteed under our assumptions. Okay, that for example, that basically u is taken like a PDF as you know it. But we may have a defective random variable, and sometimes again it's actually the way to go, as we will see. But not in this chapter, in the coming chapter. Okay. Also, m of t goes to infinity as t goes to infinity. There is a lemma here with the proof that is in the notes, which is that suppose that you have a sequence of random variables that converges almost surely to the limit big Y as n goes to infinity. So this is as n goes to infinity. Then suppose that you have something that also goes to infinity. So you have a non-negative integer valued random process that also grows without bound. Then if you replace this n by gamma of t, you also have almost sure convergence to y. Okay, so basically we have two givens. Y of n converges almost surely to y, and then gamma of t converges to infinity as t goes to infinity, and this is integer valued. So given these two, you can actually replace this small n by gamma of t, and this will converge almost surely to y. Again, the proof is in the notes. Okay, so let's now basically study sort of the convergence properties of renewal processes. First thing, we can directly apply the strong law of large numbers, since we are assuming that basically the inter-arrival times, they have a finite first moment. Okay, and so basically what is the time of the nth arrival divided by n? Well, the nth arrival is the sum of the first n inter-arrival times, and so basically by the strong law of large numbers, this will converge almost surely to the expected value of u. Now, based on the lemma that we have here, so what we can say here is that Tn over n converges almost surely to the expected value of u. Based on the lemma, then we can replace this small n by big N of t. Why? Because big N of t also grows without bound. Okay, so I can replace small n by big N of t. Okay, and by the continuous mapping theorem, you can basically take the reciprocal of both sides. So so n of t over Tn of t converges almost surely to 1 over the expected value of the inter-arrival time. And this is strictly positive because we are assuming also that u is greater than 0 with probability 1. Okay, so this is something to keep. This is something to keep in mind. Then another inequality that looks fishy, but actually it is true if you think about it. So this is the inequality. Let me copy it from here. It's here, but it's not bad actually to write it down. So again, it's one of those things, in which like you have big T and then you have N of T here, you have N of T there, And n of t itself is a random variable, and it looks like messy, and what is really going on here? The idea here is that to understand this inequality, regardless of what you choose for n of t, it is true. In other words, like, basically to understand it, I mean, the difficulty in understanding it is that n of t is a random variable, but assign any value to it, and you will find that this basically is true. So what if n of t is equal to 4? What if n of t is equal to 4? What is this inequality? It tells you that t is less than big T of 5, but is greater than or equal to big T of 4. So it tells you that if you inspect the system at time t and you find that there are 4 arrivals, then it must be the case that the 4th arrival has occurred before t, and that the 5th arrival must happen after t, because if t5 is less than or equal to t, then n of t would be 5 or more. The fact that n of t is equal to 4 means that t basically is greater than or equal to big T of 4, but is less than t5. So what if n of t is equal to 100? This inequality will tell you that t is less than t101, greater than or equal to big T100, which makes sense. Because basically, if at time t you have 100 arrivals, then arrival number 100 has occurred at a time less than or equal to t, and arrival number 101 should be after t, so that we have n of t is equal to 100. And so on and so on. So basically, n of t, yes, it's a random variable. Yes, it can be 0 or 1 or 2 or 3 or 4, and so on. And you will find that regardless of n of t, that this inequality here is true. Take the reciprocal of both of every side in this inequality, and then multiply by n of t. Okay, so we have something that looks like this. The idea of this page is that we are investigating the convergence of big N of t divided by t. So big N of t goes to, it grows without bound as t goes to infinity. T itself goes to infinity as t goes to infinity. What about the ratio? What about big N of t divided by t? So the idea here is that we are using the sandwich theorem. Okay, what about the upper bound? The upper bound, again, is what we did initially. So we started by applying the strong law of large numbers to basically the time of the nth arrival divided by n, exploiting the fact that Tn is just the sum of NIID random variables with a finite first moment. We applied our lemma, and then we applied the continuous mapping theorem, and then this thing here will converge to 1 over the expected value of u. What about this other guy here? Not a problem. I mean, this looks different. What you can do is that you can rewrite this guy as Tn of t plus 1, and in the numerator you can have n of t plus 1 to have a matching between this and that, and then you have n of t over n of t plus 1. Okay? Then, because n of t goes to infinity, then basically this thing will also converge to 1 over the expected value of u, and then you are left with the fraction n of t over nt plus 1. So a fraction of, of what is this fraction, what is the limit as n of t gets very, very, very large? It's like a large number divided by the same large number plus 1. As this guy goes to infinity, this fraction will go to 1, and so this left-hand side will also converge to the exact value, which is 1 over the expected value of u by the sandwich theorem. Now n of t over t converges almost surely to 1 over the expected value of u. Okay, so this is something. Also, small n of t. Remember this thing here. It is the expected value of n of t. Also, small n of t over t converges to 1 over the expected value of u as t goes to infinity. So we also have this result, and we need to prove it. Okay, and basically for this other limit, I will be rigorous. So I will actually prove that this limit exists that the limit of small m of t over t exists. By actually doing it the correct way, I will assume initially that we have no limit, and then we will basically study the limit infimum and limit supremum. But before we do this study, we need to basically understand, or to add to our basically bag of tricks, this thing called the world's identity. Okay, any questions? Okay, so what is the world identity, and what is something called the stopping time? And these are very important things also in the context of Markov processes, Markov chains. So the world identity, basically, it is something related to the expectation of a sum, and the number of terms in the sum is a random variable. The number of terms in the sum is not fixed, it's a random variable. Now, in a first course in probability, you may have studied something like this, with the number of terms in the sum being independent of the random variables that you are summing. But what if you have dependence? Okay, so it turns out that if there is a specific or a special case of dependence, that also is as easy as the case of independence. And this is when the number of terms in the sum is called a stopping time. So what is a stopping time? A stopping time is a random variable. Okay, so the stopping time is a random variable or a defective random variable. It can be defective random variable. Allowed to take the value plus infinity. Now, to define a stopping time, this random variable, you do not define it in vacuum. You define it with respect to a given sequence of random variables. Okay? And the indexing may start from 0, as we will do in Markov chains, but here I will do the indexing from 1. So a stopping time is a random variable that is defined with respect to a sequence of random variables. So when is this called the stopping time with respect to this sequence? So this random variable, it takes the values 1 or 2 or 3 and so on, and perhaps we will allow it to take the value plus infinity. For this random variable big V to be called the stopping time, it must be the case that the event big V is equal to tau. This event must depend only on the basically the elements in the sequence x1, x2, x3 up to x of tau. Okay, so the event that V equals tau depends only on x1, x2 up to x of tau, and is independent of x of tau plus 1, x of tau plus 2, and so forth. This must be the case. If this is true for every value tau, then basically we say that V is a stopping time with respect to the sequence of random variables x1, x2, x3, and so on and so forth. A stopping time can be defined also in terms of the event less than or equal to tau depends on x1 up to x of tau and independent of x of tau plus 1 to to infinity. Okay, and you can try again, like you can prove this equivalence, but you can take it for granted the event that V strictly greater than tau depends also on x of 1 to x of tau and independent of basically x of tau plus 1, x of tau plus 2, and so on. Okay, so you can, again, it depends on convenience, you can study any of those events. But in all cases, whether you study the event V equals tau, or V less than or equal to tau, or V strictly greater than tau, it must be the case that those events are determined by the guys from the sequence up to tau. You don't basically go beyond that. Okay, so here is a very important, I mean, so I need to provide you with an example of a stopping time, and definitely, since we are studying this in the basically when we talk about renewal processes, so let's talk about renewal processes. Let me give you an example of a stopping time with respect to a renewal process. Now, I mean, in a renewal process, what is the infinite sequence of random variables? It is basically the sequence of inter-arrival times. That's the sequence. Okay? And then what can be a stopping time? Claim n of t plus 1 is a stopping time with respect to the sequence of inter-arrival times. Not n of t. Not n of t. N of t plus 1 is a stopping time. It is this random variable that is called the stopping time with respect to the sequence of inter-arrival times. In fact, if you remove this plus 1, we no longer have a stopping time. To have a stopping time, you must add this one. So the claim is that claim n of t plus 1, that's a random variable, right? That's a random, that's an integer valued random variable, okay? And it is a stopping time with respect to the sequence of inter-arrival times u1, u2, u3, and so on. Why? And why nt plus 1? Why not just nt? So the idea is basically do the test of stopping time. Okay, so let's now study the event n of t plus 1 is equal to m, which is equivalent to that n of t is equal to small m minus 1. Now, what do you need to know to make sure that this event or this statement n of t is equal to small m minus 1 is true or false? How can you check that big N of t equals m minus 1 is indeed the case, or it cannot be the case? What are the inter-arrival times that if you know them, you can judge this proposition and assign to it either true or false? So this statement tells you that the number of arrivals at time t is exactly m minus 1. So if I give you u1, u2 to the second arrival, u3, okay, and then um minus, so, and then somewhere here um minus 1, and then um, okay, so those are the m inter-arrival times. Okay, how can you check that n of t is equal to m minus 1? Well, if you know those guys, and if t is here, if t is somewhere here, then this event is true. If t is not here, then you are sure that this event is false. You are able to assess this event using inter-arrival times from u of 1 up to u of m. And this is exactly what is needed to define basically a random variable, here in our case n of t plus 1, as a stopping time.